Welcome back. So, in our last class we have talked about DC potentiometer and we have measured unknown DC voltage. In this class we will talk about AC potentiometer, and I hope the calibration and measurement phase was clear to you. Otherwise, it will be difficult to understand this class. Okay. Now, the first difficulty that we have when measuring AC voltage with potentiometer is that there is no standard AC cell. Okay. So, we do not have a standard AC source which we can rely on, I mean whose value does not change with any factor in, so there is there is no such reliable AC source, okay, which we can call as standard. So, this is the difficulty, and in this talk in this class we will see how to use DC standard cell to measure unknown AC source using potentiometer. So, what we will do? Okay. So, let us first draw the this is the long wire of the potentiometer with uniform cross section. Now, we want to measure a unknown source which is AC. So, let us draw the unknown source. So, this is a unknown AC source. Okay. So, the way to connect it is of course like this: connect one side to one terminal of this potentiometer wire, another side to a galvanometer, and we will use a jockey which can move along this wire, so that we will find the null, and by noting the length from one side to the jockey, we will find the value of the EMF. That is the way we do it, right. But now we need a supply, a voltage supply here, without which it will not work. So, that is the main thing. So, let us put a voltage supply. So, this is connected across the two ends of the potentiometer. Now, this source must be AC, right. This must be also AC, because if this is not AC, then the potential drop here will also not be AC, and then we cannot get a balance. If this is DC, a DC cannot balance a AC. Okay, a DC voltage can never be equal to a AC voltage. And also, another important thing we need is that the frequency of this AC source must be same as the frequency of the unknown source. Okay. So, important point, the frequency of the supply voltage, by supply I mean this, okay, call this Vs. Frequency of the supply voltage Vs must be same as the frequency of this unknown voltage, call it Vx, must be same as the frequency of Okay, else we'll never get a balance. Okay. Now, you also have seen that in case of DC, we actually use another standard voltage source, and then we first do the standardization by connecting this galvanometer initially to this. Okay, so we may have a switch. So in the standardization phase, if you recall what we did in case of DC, we first connect it to the standard cell, and then we set this to a desired length, okay, a convenient length, and then we adjust the current through the wire. So for that we need a rheostat. Okay, so you can also draw a rheostat maybe like this if you like. R1. So calibration step is calibration. So it means put the jockey at a convenient length, put the jockey at a convenient length. Okay, do not move the jockey and do not move it anymore. Instead, adjust R1, adjust rheostat R1 to get null at that convenient length. That's what is calibration. But as I already have said, the problem is we do not have a standard AC source. If we had a standard AC source, we would have done this in the same way like we did for the DC. Okay, but we do not have a standard AC source. So what we do is this: we instead connect a DC source, standard DC source, ESTD, okay, and we connect the jockey here. So put it at say K1, okay, switch, call this switch as K1, and this is position 1, this is position 2. So I can write K1, switch K1 is at position 1, okay, during the calibration. And then, okay, we will put the jockey at a convenient length. So whatever length we choose, okay. So for example, if this is 1.08 volt, so we may choose say this length, okay, this convenient length to be say 108 centimeter, okay. For example, we can choose this as 108 centimeter. So which will imply that 1 centimeter is 0.1 volt. Okay, so choosing 1 centimeter is equal to 1.08 volt by 108 centimeter, which is 1 by 100, so 0.01 volt per centimeter. So this is the choice we have made for calibration. For example, you can do it, okay. But now there is a problem. The problem is this is now DC, this is AC. We can never get a balance, okay. So we can never get a balance, therefore we also need a DC source here, but we need a AC source for measuring this unknown. So therefore we will have two sources. Okay, so we will have another DC source and say we can connect this, there is a key say which can connect between this, call this key as K2, position 1 and position 2. Okay, so during calibration therefore we must have so we should have K1 at position 1 here. So the galvanometer is connected to the standard cell, and K2 at also position 1. Now the supply is also connected to this battery DC. Okay, so this is at position 1, this is also at position 1. Now you choose a convenient length which we have chosen like this. So we put this at 108 centimeter for example. This is an example only. Okay, and we adjust R1 until we get the null. Okay, and once we get the null, after we get null, then 1 centimeter will be equivalent to 0.014. 1 centimeter will be equivalent to 0.01 volt. This is calibration step. Now we will go to the measurement step. But before we can go there, we need another important thing. We need an ammeter A, okay, and this ammeter should work both with this DC and AC. So this can be like an electrodynamic meter. Okay, so this ammeter, let me write here, ammeter A should work with both DC and AC. So like electrodynamic meter. So this will indicate, so this the ammeter will indicate, the ammeter will indicate the RMS value. Okay, so the ammeter will indicate the RMS value, not the average value, because this is a AC meter which works both with AC and DC. Okay, so this is important. Okay, so we will do one more thing in the calibration phase, which is we will record or note the value of the ammeter A. Call this value is, say the current is IC. Okay, say this current is IC, current during calibration. Okay. Now in the measurement phase, what we will do, of course we have to go to the unknown source. So switch K to K1, so this switch K1 will be K1, we have to move it to position 2, and this switch, now this is AC, so here we also need an AC, so this also will be moved to position 2. So K2 at position 2. Okay, so this is in the measurement phase. Okay. Now what we will do, we will adjust rheostat R1 until the ammeter reading is same as IC. What is IC? It is the RMS current which was flowing through this wire during the calibration. Now in the measurement phase, when we have changed everything, the source is changed here, here also the source is changed. Now we will adjust this rheostat once again so that we get the same value of current IC. Now if we have the same value of current IC, okay, but previous IC was DC, now this IC is AC, okay. So by when I say that same current IC is flowing, it means the RMS value of the current is same, okay. Actually one current is DC, another current is AC, but their RMS value is same. So it means the RMS value of the AC current which is flowing now is same as RMS value of the previous DC current. If so, okay, if that is the case, let me write here now. Okay, so this ensures that, so if same RMS current is flowing, then the RMS value of the voltage across this wire is same. Although previously it was DC, now it is AC, but their RMS value is same. So that means the RMS value of the voltage, AC voltage across the potentiometer pot in short is same as the previous RMS value, previous DC RMS value, right. Now for DC, RMS is same as the average or the DC value itself. So therefore we can say that the RMS value of this voltage, okay, here to here is same as the DC voltage which was here previously. Or we can also say the RMS value per unit length of this wire is same as the DC value which was there previously per unit length of the wire, right. So RMS voltage per unit length will be same as the previous DC voltage per unit length. Which is same as this 0.01 volt per centimeter by choice. This is what we have chosen. Okay. So now we can say therefore in this wire each centimeter represents 0.01 volt RMS. So now we have 1 centimeter is equivalent to 0.01 volt RMS. Right. Okay. So if so, now we can adjust. So now this key is at is connected to this unknown source. So now we can adjust the position of this jockey to find the null with this unknown source, and that will give us the value of the unknown source. So now in the measurement phase, adjust jockey to get the null. If we get the null at a length L, okay, from the left side, then RMS value of the unknown source which is Vx RMS will be same as this length L multiplied by, if this is L centimeter, multiplied by 0.01 volt RMS. So, this will be 0.0, I mean whatever this is. So, this way we can measure it. So, this is the trick. So, the problem was there is no standard AC cell, no standard AC source. So, by intelligently using this DC cell to calibrate this wire, we actually have, we actually have made this potentiometer useful for AC as well. Okay. So, this is the trick for using AC sources. Now, I will conclude this video, this class with a question. The question to you is that we have said that this supply voltage and this unknown voltage must have same frequency, otherwise we will not get balance or null at all. But is that enough? What if this supply voltage and this source, so this supply voltage and this unknown source has different phase angle? So, the question is the frequency of Vx and Vs are same, but if the phase angle of Vx and Vs are not same, can we get null at all? So, if Vx is like this and if say Vs is like this, same frequency, but they have a time delay between them, time difference between them. So, they do not reach their peak and 0 simultaneously. So, can we ever get a null? I think no. So, think of this and we will in our next class start our talk with this question. Thank you.